Chemical engineering is a multidisciplinary field that brings together chemistry, physics, and mathematics to design and operate processes for transforming raw materials into useful products. It's a dynamic and versatile profession that plays a crucial role in industries ranging from pharmaceuticals and energy to consumer goods and materials science. As chemical engineers, we leverage our understanding of chemical reactions, fluid dynamics, heat and mass transfer, and other fundamental principles to develop innovative solutions to complex challenges. Our work often involves designing and optimizing manufacturing processes, improving product quality, enhancing efficiency, and ensuring safety and environmental sustainability. Whether you're interested in developing new medicines, designing more efficient energy systems, or creating advanced materials, chemical engineering offers a wealth of exciting opportunities. Chemical engineering applies scientific principles to solve problems in the production and design of materials and processes. Chemical engineers are essential in the design, construction, and operation of large-scale industrial plants, factories, and refineries to manufacture chemicals, pharmaceuticals, and other products. They work on research and development to improve existing processes and develop new technologies, tackling challenges in areas like sustainable energy, environmental protection, and healthcare. Chemical engineering involves the development of new materials, products, and processes by combining science and engineering. The roots of chemical engineering can be traced back to ancient civilizations, with early practices like brewing, pottery, and metallurgy laying the groundwork for the field. The 18th and 19th centuries saw significant advancements in chemical processes and manufacturing, driving the need for a dedicated field of study. In the late 19th and early 20th centuries, chemical engineering emerged as a distinct discipline, with the establishment of dedicated academic programs and professional societies. This timeline highlights the evolution of chemical engineering, from its ancient origins to its formalization as a field of study. Chemical engineering is a broad field that encompasses several fundamental principles. Stoichiometry is the quantitative study of the relationships between reactants and products in chemical reactions. It allows us to predict the amounts of substances involved in a reaction. Thermodynamics deals with the flow and transformation of energy in chemical processes. It helps determine the feasibility and efficiency of reactions and processes. Transport phenomena describe the movement of heat, mass, and momentum within chemical systems. This knowledge is crucial for designing effective industrial processes. Kinetics is the study of the rates and mechanisms of chemical reactions. It allows us to predict reaction times and yields. These four principles, stoichiometry, thermodynamics, transport phenomena, and kinetics, form the core of chemical engineering and are essential for understanding and designing chemical processes. Mass and energy balances are foundational concepts in chemical engineering, based on the principles of conservation of mass and energy. These balances are essential for analyzing and designing chemical processes, optimizing their performance, and ensuring safety. They help engineers understand material usage, energy consumption, and how these factors change throughout a process. Mass and energy balances are crucial for process design, equipment sizing, and other key aspects of chemical engineering. By applying these balances, engineers can make informed decisions to improve the efficiency and effectiveness of chemical processes. Chemical thermodynamics is the study of energy changes that occur during chemical reactions. It helps us understand and predict the feasibility and spontaneity of chemical processes. Key concepts like enthalpy, entropy, and Gibbs free energy are used to analyze the energy changes. The equilibrium constant K quantifies the extent to which a reaction goes to completion at equilibrium. Thermodynamics has many practical applications in chemical engineering, such as process design, reactor optimization, and phase equilibrium calculations. The colorful diagram illustrates these thermodynamic principles in a visually engaging way. Transport phenomena is a broad field that encompasses the study of momentum, heat, and mass transfer. These three core areas, momentum, heat, and mass transfer, are fundamental to understanding and designing many types of systems and processes. Momentum transfer describes the motion of fluids and the forces acting upon them. Heat transfer deals with the flow of energy as heat, through mechanisms like conduction, convection, and radiation. Mass transfer focuses on the movement of chemical species within a system, such as through diffusion and convection. These transport phenomena have wide-ranging applications in designing reactors, separation processes, heat exchangers, and more. Understanding and being able to model these transport processes is crucial for engineers and scientists working in a variety of industries. Fluid mechanics is the study of how fluids, like liquids and gases, move and interact with their surroundings. It explores important concepts like pressure, viscosity, and buoyancy that are crucial for understanding fluid behavior. Fluid mechanics has many important applications in chemical engineering, such as designing and analyzing processes involving fluids. This includes things like piping systems, pumps, reactors, and separation equipment. Understanding fluid mechanics is essential for developing effective and efficient chemical processes and equipment. Heat transfer is a fundamental concept in engineering, involving the movement of thermal energy through various mechanisms. The three main modes of heat transfer are conduction, convection, and radiation. Conduction is the transfer of heat through direct contact between molecules, with the rate depending on the material's thermal conductivity. Convection is the transfer of heat through the movement of fluids, which can be natural or forced. Radiation is the transfer of heat through electromagnetic waves, which can occur even in a vacuum. Heat transfer plays a crucial role in many important engineering processes, such as power generation, refrigeration, and chemical processing. Understanding and effectively managing heat transfer is essential for designing efficient and reliable systems across a wide range of industries. Mass transfer is the movement of a substance from one location to another, driven by differences in concentration, pressure, or temperature. It's a crucial process for many important chemical and industrial applications, like distillation, absorption, and extraction. The two main types of mass transfer are molecular diffusion and convective mass transfer. Mass transfer has applications across a wide range of fields, including environmental engineering, food science, and biotechnology. The key points to highlight are the definition, importance, types, and applications of mass transfer. Reaction kinetics is crucial for optimizing chemical processes. It involves studying the rates and mechanisms of chemical reactions. Key concepts include reaction rate, rate law, reactor design, and reactor types. Reaction rate is the speed at which reactants transform into products. Rate law is the mathematical expression describing how reaction rate depends on reactant concentrations. Reactor design involves choosing the optimal reactor type and operating conditions for a specific reaction. Common reactor types include batch, continuous, plug flow, and stirred tank reactors. Careful reactor design can help maximize product yield and minimize costs through process optimization. Process simulation allows us to model and analyze processes digitally before implementation, helping to optimize performance. Optimization techniques use mathematical methods to identify the best operating conditions and minimize costs. Process control systems maintain consistent, efficient operation through automated monitoring and adjustment. Sustainability is a critical consideration, with the goal of minimizing environmental impact through efficient resource use. These four elements: simulation, optimization, control, and sustainability are all crucial for designing and operating high-performing, cost-effective, and environmentally responsible processes. Unit operations are the fundamental building blocks of chemical processes. They involve physical or chemical changes that are combined to create larger industrial processes. These operations are used across many industries, from pharmaceuticals to petrochemicals. Common examples include distillation, filtration, extraction, mixing, and heat transfer. These unit operations are essential for separating, purifying, and transforming materials in chemical processes. Understanding these fundamental building blocks is key to designing and optimizing complex chemical plants and systems. Distillation is a crucial unit operation in chemical engineering, used to separate components of liquid mixtures based on their boiling points. It's widely used in industries like petroleum refining, pharmaceuticals, and food processing. Different distillation techniques like fractional distillation and steam distillation are used to achieve specific separations. The choice of technique depends on the mixture's composition and the desired purity of the separated components. The image shows a distillation column, a key piece of equipment in the distillation process, with steam rising through the column and liquid flowing down. The industrial, realistic scene emphasizes the detailed nature of the distillation process. Absorption and adsorption are two key processes used in chemical engineering. Absorption is when a gas or liquid dissolves into a liquid solvent. Adsorption is when a gas or liquid sticks to the surface of a solid material, forming a thin layer. These processes are important for separation, purification, and reactions in chemical plants and processes. The image shows a chemical plant with a tall distillation tower, surrounded by pipes and equipment. This is an example of where these processes would be used. Absorption and adsorption have different mechanisms. In absorption, the molecules penetrate the liquid, while in adsorption they stick to the solid surface. Membrane processes are essential for separating and purifying substances in a wide range of industries like pharmaceuticals, food processing, and water treatment. They offer diverse applications, from separating solids from liquids to purifying water and removing impurities from gases. Membrane technology is a dynamic field with ongoing research to improve performance, efficiency, and expand its applications. These processes are highly versatile and play a crucial role in many industrial and commercial settings. Crystallization is the process where a solid forms from a solution, involving supersaturation and nucleation, followed by crystal growth. Precipitation is a similar process, but it occurs when a solid forms from a liquid or gas mixture due to a chemical reaction. Both crystallization and precipitation are widely used in chemical engineering for separating and purifying materials. Examples include salt production from seawater and the production of pharmaceuticals. Drying is the process of removing moisture from solids, often using heat to vaporize water. Evaporation involves changing a liquid to a vapor, usually by heating. Common drying and evaporation techniques include spray drying, tray drying, and freeze drying. These processes are essential for many industries like food, pharmaceuticals, and chemicals. Drying and evaporation allow us to preserve products, concentrate solutions, and create powders and other dry forms. The specific techniques used depend on the material and the desired final product. Mixing and agitation are fundamental processes in many industries, from pharmaceuticals to chemicals. These techniques are essential for blending components, creating homogeneous mixtures, and ensuring consistent product quality. Controlling fluid motion and enhancing mass and heat transfer are key aspects, as they impact product quality and reaction rates. Mixing and agitation are widely used in a variety of industrial-scale operations, across diverse sectors like food processing, manufacturing, and more. Understanding the principles of fluid dynamics and leveraging these techniques can lead to significant improvements in process efficiency and final product characteristics. Particle size and shape are fundamental properties that impact a material's behavior and performance in various processes. Understanding the distribution of particle sizes is crucial for optimizing processes like filtration, grinding, and mixing. The surface area and porosity of particles influence their reactivity, adsorption capacity, and mass transfer characteristics. Particle packing and flow behavior are critical in determining the efficiency of processes like fluidization, sedimentation, and conveying. Process instrumentation and control is a critical aspect of industrial operations, ensuring efficient and safe processes. Sensors and transducers are the foundation, measuring key process variables like temperature, pressure, flow, and level, and converting them into electrical signals for processing and control. Control systems use feedback loops to maintain desired process conditions by adjusting actuators like valves, pumps, and heaters. This allows for precise control and optimization of the process, improving productivity, quality, and safety. Computer-aided process engineering is a field that uses various software tools and technologies to simulate, model, analyze, and automate industrial processes. Simulation software allows engineers to virtually test and optimize process designs before implementation, improving efficiency and reducing costs. Process modeling involves creating mathematical representations of real-world processes, which can be used for design, troubleshooting, and optimization. Data analysis techniques are used to collect and analyze process data, providing insights to improve operations and control. Automation through process control systems and robotics enhances efficiency and productivity in industrial settings. These technologies work together to enable engineers to design, operate, and optimize industrial processes more effectively. Chemical engineers play a crucial role in developing and implementing sustainable processes to minimize environmental impact. They assess the environmental impact of chemical processes, identifying potential risks, and finding solutions to minimize pollution. Chemical engineers work on waste reduction, resource recovery, and pollution prevention, ensuring responsible production practices. Engineers contribute to the development of renewable energy sources, promoting sustainable practices, and reducing reliance on fossil fuels. Biotechnology and bioprocessing are crucial for producing a wide range of important products, from pharmaceuticals to biofuels and food ingredients. Microorganisms and cell cultures are the workhorses of biotechnology, used to synthesize valuable compounds and modify biological processes. Genetic engineering techniques allow us to enhance the capabilities of these organisms, leading to improved bioprocessing outcomes. Bioprocessing is an inherently sustainable approach, utilizing renewable resources and minimizing environmental impact. These four key areas: applications, microorganisms, genetic engineering, and sustainability, are the foundations of this powerful field. Fossil fuels like coal, oil, and natural gas have been the dominant energy sources for the world, powering our economies for centuries. These fuels are formed from the decomposition of organic matter over millions of years, making them a finite resource. Renewable energy sources like solar, wind, and hydropower can be replenished naturally and are becoming increasingly important as we transition to a more sustainable energy future. Biofuels derived from living organisms like plants and algae are another renewable option that is gaining traction. Nuclear energy is a powerful source, but it also comes with safety and waste disposal concerns that need to be carefully managed. The image on this slide provides a high-level overview of the various energy sources and how they are interconnected, highlighting both traditional and emerging options. Materials science is the study of the relationship between the structure and properties of materials. Understanding this relationship is crucial for selecting and designing materials for various engineering applications. By manipulating a material's structure, we can tailor its characteristics to meet the specific needs of modern technology. This field investigates how materials are formed, how their microstructure impacts performance, and how they can be engineered to have desired properties. Principles from materials science guide engineers in choosing the right materials and optimizing their design for reliability and effectiveness. The connection between a material's structure and its properties is the foundation of this discipline, allowing us to develop new and improved materials. Chemical processes involve potential hazards that must be identified and understood. This includes understanding the properties of chemicals, the equipment used, and the potential for accidents. Once hazards are identified, safety measures are implemented to prevent accidents. This could include safety equipment, procedures, and training programs. Various hazard analysis techniques are used, such as HAZOP, PHA, and FMEA, to systematically identify and assess risks. As chemical engineers, we have a responsibility to uphold the highest ethical standards in our work. Integrity and honesty are core values that must guide our actions. We must avoid any conflicts of interest that could compromise our objectivity. Our work has a profound impact on the environment and public health. We must always be mindful of these consequences and use our knowledge responsibly. Maintaining our expertise through continuing education and professional development is critical. This allows us to stay informed about evolving ethical and professional standards in our field. Chemical engineering is a versatile field with many potential career paths. In research and development, chemical engineers create new products, processes, and materials. They can design and optimize chemical processes to ensure efficiency and safety. Many chemical engineers progress into management roles, leading teams and projects. Chemical engineers can also provide expert advice and guidance to companies in various industries as consultants and project managers. Chemical engineering is a dynamic field that requires continuous learning and development to stay current and competitive. Professionals have a variety of options to engage in continuing education and professional development activities. Joining professional societies like AICHE allows you to connect with peers, access the latest industry knowledge, and stay up to date. Continuing education courses can help you enhance your expertise in specific areas like process design, safety, and environmental regulations. Attending conferences and workshops is a great way to network with industry experts and learn about the latest trends and best practices. Online learning platforms offer flexible and accessible professional development opportunities that you can fit into your schedule. By actively pursuing continuing education, you can improve your skills, advance your career, and contribute to the growth and progress of the chemical engineering field. The chemical engineering field is constantly evolving, driven by the needs of society and technological progress. Emerging innovations in areas like sustainable energy, material science, and biotechnology present exciting new opportunities for chemical engineers to make a positive impact. These advancements offer the chance for chemical engineers to contribute to a better, more sustainable future. While the field continues to advance, the core principles and problem-solving skills of chemical engineering remain foundational. As we look ahead, chemical engineers will play a crucial role in addressing global challenges and shaping the technologies of tomorrow.